Assalamualaikum warahmatullahi wabarakatuh. In this video, you will be looking at some of the common applications of integration, and we will start off with some classic problems in physics that are related to distance, velocity, acceleration, and work, and then we will continue with finding the area between curves and finding the volume of a solid. So before we start off with the applications of integration in physics, let's consider the important principle where you have this integral of a rate of change is the total change, and it can be represented mathematically as such. Okay, so I'm going to explain the idea of rate of change. So rate of change is the derivative. You have seen this in the previous chapter, in chapter 4. So you've been talking about the rate of change, which is the first derivative, and it can be represented as this one, f prime x. And so if you consider finding the integral of a rate of change, which is given by this mathematical expression here. So this is the integral of a rate of change from point A to B. The result that you will get is the original function, which is the function f. So fb minus fa is the function evaluated at point B and point A, and then you take the difference between the results here. So when you consider the difference, then this is essentially saying you are talking about finding the total change. So as an example, if you have this function here, this is a volume of water in a reservoir at time t, then its derivative, so this is the derivative, which is v prime t, is the rate at which water flows into the reservoir at time t. So if you consider the rate of change here and you find the integral of that from t1 to t2, the result that you will get here is this one. So you will get back the volume of water, you will get back this function here, and this volume of water will be evaluated at time t1 and t1 and t2. So after that you will find the difference between these two. So the difference here represents the change in the amount of water in the reservoir during that time interval. Now, as a second example, if you have the rate of growth of a population represented by this, so this is the first derivative, so it represents the rate of a growth of a population, and when you consider this into here and you want to find the integral of that from point t1 to t2, the result here that you have is the difference between the population at time t2 and t1. So that essentially presents the increase in population during that time period. So we are going to take this principle here and applies to a problem found in physics, a common problem, which is related to having an object that moves along a straight line. So when you have this object, you can actually describe the position of the object using a function. So we can call this function st. So this function depends on time t. You have seen in the previous chapter the idea of its first derivative. So when you find the derivative of this function, so s prime t is the first derivative, the result that you get here represents the velocity of a particle at time t. So if you consider the velocity into this, so you consider finding the integral of velocity from time t1 and t2, the result that you will get is this function back, which is st. This is the position function. So you will get this function here, and this function will be evaluated at time t2 and t1, and the difference of that represents the change of the particle during that period of time. So another name for that is what we call the displacement of a particle. Now, I'm going to explain the idea of distance and displacement, using this simple figure that I have over here. So let's say you are interested to move from point A to point B, and you are actually taking this curvy road or curvy path from point A to point B. So the distance is a measurement, is the exact measurement of the path that you take from A to B. So distance is the measurement of the exact path or exact road that you take from A to B. So that's distance. On the other hand, if you talk about displacement, displacement is you can think of it as the shortest distance from point A to point B. So from point A to point B, you can easily go in this direction. So that is displacement. So you have to remember that distance is considered as scalar and displacement is a vector. So it has magnitude and it also has direction. Okay, now the formula that you have seen here, so this is the formula that you have seen here. This is the formula that you can use if you are interested to find what's the displacement of the particle. Okay. On the other hand, if you want to find the distance traveled by the particle, then you can find using this formula here. Now, what is interesting about this formula here is that you have to make sure the velocity here is positive. The function given here is positive, and that's why we have this absolute value sign that you see here. So this is to make sure that the velocity function is always positive, and then once you have managed to do that, the result that you have here will represent the distance traveled by the particle. Now I'm going to illustrate to you the idea of this, the difference between finding displacement and finding the distance traveled using this figure, which I think can be adjusted to fit our given scenario here. Okay, so if you see on this figure here, I can say that instead of y, let me just be specific, this may represent our velocity function, and this represent the time, which is t. And since t begins from 0 to onwards, t is a positive value, so we actually do not need this part here, so this is not needed. So we're just going to consider the graph from 0 onwards. Okay, so so this is the graph that we are going to consider. So from this point onwards. Okay, right. So now I'm sure you have seen or I hope you still remember what you have seen in the previous video. The idea related to integral, which is if you want to find the integral of a function evaluated from A to B, so if you have the curve is positive, fx here is positive, then the integral from A to B here represents the area under the curve, which is going to be positive. On the other hand, if you have fx that is negative, therefore the integral evaluated here will give you a negative result, so the area here is going to be negative. And so if you have a combination of function that has positive and negative, so this is the positive part, this is the negative part, the integral here will represent the difference in the areas, so the result can be negative. Okay, so it represents the difference in areas, and that's what we are doing here for displacement. Okay, so velocity is a function that can be positive and negative. So because of velocity being a vector, so velocity here is a vector, and it has magnitude and it has direction. So velocity has magnitude and it has direction, which can be represented as using the positive sign or negative sign. So that represents the direction of a particle. So when you talk about positive value here, that means it's moving to the right. Okay, it's moving on one direction, and if it becomes negative, that means the direction is reversed to the other side. Okay, so that's the idea of positive and negative velocity. So therefore, if you integrate, for example, from point t1 until t2, so let's say the integral is from point t1, so let's say this is t1, so let's say this is t1, and let's say this is t2. So if you integrate velocity function from that point, so what you get here is the area under the curve, and that represents the difference in the areas. So you will get the difference in the areas, which is displacement. Okay, on the other hand, the distance, the velocity here has to be always positive, because when you talk about distance is a scalar, so it doesn't consider direction, whether positive or negative. So what you need to do is you have to make sure that the function that you see here, so we're going to have a problem here because this is a negative value. So this is a negative vt, velocity here is negative, so you need to transform this part to be positive. So that can be easily transformed into positive if you consider y is equal to negative fx. I hope you do remember this. This is what you have seen in chapter 1, where you can reflect the graph on x-axis. So when you have negative fx, that means the graph will be reflected on x-axis. So this is x-axis. So if you have the graph that looks like this, and you consider the negative sign of fx, so then the graph can be reflected in this manner. So it is reflected along the x-axis. So for this one, since this is a negative value of velocity, by considering negative of this function, you'll be able to get the same graph which will be reflected on x-axis here. And by doing that, you will get by finding the integral of this function, of the new function which is positive, okay, taking the absolute value of vt, then you will get an area which is also positive, and you can add up these two areas here and obtain the total distance traveled by the particle. Okay, so that's the second problem. So we have seen the first problem, which is to find the displacement, the second problem, which is to find the distance traveled. Next is you might be interested to find the velocity, the change in velocity from time t1 to t2, and that requires the implementation or the use of AT. So AT is the acceleration of a particle. You can use it and find the integral of that. So if you find the result of this, you will get volume. Okay, so when you integrate acceleration, you will get volume evaluated at time t2 and t1. So the difference of this is the change in velocity from time t1 to time t2. Alright, I think that's all for now. Thank you very much for watching, and I will continue with more example in the next video.